Start the recording. Yes, okay. So please, the floor is yours.
Great, thank you very much. So, for those of you who have never met, hello, I'm Francisco. I'm a postdoc at Max Planck Institute for Gravitational Physics, also known as the Albert Einstein Institute. And I've been working mostly on environmental effects for LISA sources with a focus on extreme mass ratio inspirals. And that's mostly what I'm going to talk about today. This will be a miscellaneous of a series of my work that I've been doing for the past year and that I try to congregate in just one talk. This is an online talk, so I will try to be very pictorial and simplistic so that you don't feel bored. Feel free to interrupt me at any time if you have any question. So let's start by the title. I suppose most of you know what an EMRI is, but in any case, EMRIs are one of the main scientific goals of LISA, their observation and study. They are binaries where we have a very light secondary object with at most a few solar masses, like a stellar mass black hole or a star, that's orbiting around a much more massive supermassive black hole, typically present at the galactic center, so that the mass ratio is very asymmetric. And because of that, these systems are not very suited to be tackled with traditional techniques from numerical relativity. And instead, what people in the Cell-Force program do is to try to solve this relativistic two-body problem via an expansion of the Einstein's equations in terms of this small mass ratio. And EMRIs will perform thousands of orbital cycles while in the LISA band, meaning that if we are able to accurately track their evolution throughout the inspiral, we will be able to impose very strict tests in the theory, because we will be able to measure the intrinsic parameters of the system with relative precision of 10 to the minus 4, 10 to the minus 5, and this is an improvement of 1,000 orders of magnitude with respect to what we are able to do now on Earth. But as you could see from this initial picture, EMRIs also have extremely complex trajectories, and this corresponds to one of the hardest problems for both modeling and data analysis for LISA. Now, to make things a little bit even more complicated, we don't know really how many EMRIs we will observe. So the standard formation picture for EMRIs is that we have two bodies that are scattering from each other, and one goes into a very high eccentricity orbit towards the central supermassive black hole. As it goes along, it will emit gravitational waves, and potentially it could circularize so that it becomes a compact binary. This means that for these kind of formation mechanisms, EMRIs can have arbitrary inclinations, and they can enter in bands with eccentricities as high as 0.7. But there are other ways to form EMRIs, where we take into consideration the interactions that there are with other structures around our supermassive black hole. So galactic centers are not typically pure vacuum. Around the supermassive black hole, there will be a population of compact objects. There could also be a disk that could be very dense if the black hole is actively accreting. There should be also a dark matter structure. And all of this should also influence the way that a body moves around our supermassive black hole. So imagine the case where we have one of these scatterings from a large distances, and then as the body goes on and on from the disk, it will interact with it in some kind of way. This should alter its trajectory and could also alter the number of EMRIs that we have per supermassive black hole. And indeed, this has been quantified in recent years, and the typical picture is that the presence of these astrophysical environments boosts EMRI formation rate per individual black hole by a couple of orders of magnitude. And this is more or less intuitive in the sense that typically this presence of these additional structures contributes to more dissipation of angular momentum, which promotes binary formation in comparison to a pure plunge that comes from one of these eccentric trajectories. Now, if we expect from our observations that around 1 to 10% of supermassive black holes is actively accreting, so it has one of these dense disks around that, then 0.1 times 10 to the 1 or 10 to the 3 gives you something of order 1 to 10, which means that this kind of formation channels then becomes competitive for LISA. So we should try to understand in a little bit more in depth how the presence of these disks affects the evolution of the binary, and it could lead to something observable in the gravitational wave signature of these systems. So let's take, before that, let me just say that we are already observing systems of this type, or we think we are observing systems of this type. So from a couple of years ago, there are a dozen of soft X-rays periodic observations in the electromagnetic spectrum. And it has been conjectured by different people using different models, that these bursts, these quasi-periodic eruptions, as they have been called, correspond precisely to the passage of our small secondary through a disk around a supermassive black hole. And in fact, you can try then to see how much the period between the disks changes throughout the years, and you can try to adjust some kind of interaction with the disk to it, or even gravitational wave reaction to see if it follows that trend. So these are very recent observations, and I guess during the next decade, until LISA flies, we'll have much more of those and with greater precision. Now let's take the case, precisely the case where we have a supermassive black hole, we have an accretion disk around it, and now we are putting our small black hole orbiting around a supermassive black hole. So the question that we want to understand is, how is this different from pure vacuum? So first, there will be matter that is infalling onto the supermassive black hole and infalling onto our secondary. This will increase their masses, so it should change the dynamics throughout the spiral. Between the two black holes, there's also additional matter. This changes the gravitational potential, again, changing the dynamics. And also, as you can see in this simulation, numerical simulation of this system, as the body is piercing through the disk, it is generating these sections of overdensities. So we are seeing the density normalized by some number. And these overdensities then will trail behind the movement of the secondary. Because the disk itself has a differential rotation, these overdensities actually form a spiral arm structure that you see here propagating, and this will then recently interact with the binary at some specific locations, and recently exchange angular momentum with the binary, which can either accelerate or stall how fast the spiral occurs. So this mechanism here is what people call planetary migration from the formation of protoplanetary disks, and here we are applying it to the case of extreme mass ratio inspirals. So more than 10 years ago, in a seminal paper by Coxis, Yunis, and Loeb, they tried to quantify using very simple models how important these different effects were, and they found that disk-induced migration, so this is what I just call planetary migration, provides the dominant perturbation to the spiral, with other effects like accretion of mass from the disk, or just aerodynamic drag being also potentially observable. Now, this has motivated people in recent years to try to repeat these studies using more sophisticated tools, more in line with what we'll actually do for LISA. And there's this paper by Lorenzo Sperry, Laura Spernam, and other people from LEX a couple of years ago, that they consider one of these corrected inspirals from planetary migrations for a typical EMRI that we will observe with these parameters. And then they just ran Bayesian MCMC to try to infer how well we could constrain this additional dissipation mechanism that is introduced by the presence of the disk. So in their case, they use a very simplistic model for migration. This is just a power law with some amplitude and a slope. The amplitude depends on the properties of the disk, so its density, its height, and so on. And the power slope depends on the intrinsic thermodynamics. So for the typical, what is called the Shakura-Sunaev alpha disk, which is the most popular analytical model for an AGN disk, this n corresponds to 8. And you can see that If the amplitude is large enough, you could actually constrain this additional torque, and then you can try to infer the properties of the disk from these measurements. And in fact, they also discovered that if we didn't include these additional corrections to the evolution of the binary, you could completely miss out the EMRI in 4 years of observation, or even if you do it in a smaller observation time, you'll have bias intrinsic parameters, which could potentially jeopardize tests of fundamental physics that you want to do with these systems, because those require very precise measurements. Now, I've been talking for the case of accretion disks, but in fact, this can be applied to any astrophysical environment that you consider. It will also be for dark matter. So the rationale that is behind this type of problem is that the EMRI is surrounded by the environment, the binary interacts with the matter, this changes the trajectory, it changes the gravitational signature of the binary, and then the question that we want to address is, by doing the proper modeling, is that are these effects so strong that we can learn something about the astrophysical environment where they are evolving, or if they are not very strong, can they actually undermine some kind of science that we want to do apart from the astrophysics? So this is what is behind all of these environmental effects business. Now, I always like to put some kind of slides to motivate my work apart from stuff that I've done or other people have done. And in this case, I've been bringing a print screen from the LISA Red Book, where you can see there's an entire science objective that is dedicated precisely to environmental effects. And the highlights that I took from that is this square in blue here that says that the emerging picture is that environmental effects will be detectable in a variety of realistic astrophysical scenarios, and even a successful measurement will provide invaluable information on the presence of matter in the form of stars, gas, or dark matter only a few Schwarzschild radio waves from the massive black hole horizon. So it's certainly a problem that has been gaining a lot of momentum in recent years. I think this is explicit from the number of talks that appear now on this topic in conferences and also just papers that you see on arXiv. And I think it will be continuing to grow during the next decade until LISA flies. Now, there's an easy way to actually quantify that these environmental effects will be important for LISA. So in the beginning of my talk, I said that the self-force program tries to solve the relativistic two-body problem by doing an expansion in the mass ratio of the Einstein field equations. For the purposes of LISA, this expansion has to be done up to second order in mass ratio, so up to epsilon squared when you expand the metric. And then you can compare what is the magnitude of these second order self-force corrections to the spiral with respect to our environmental effects. This is what I'm plotting on this plot here. So I'm including the rate of dissipation of the orbital separation, so of energy, of angular momentum, what you want, of different effects, different beyond vacuum GR effects with respect to self-force corrections, which are the second order self-force corrections, which are the dotted lines. And you can see that for amplitudes that were similar to the ones that I just showed for that study of the MCMC with migration, for large orbital separation, the environmental effects will actually dominate with respect to second order self-force. And this is a typical behavior of environmental effects. So they are negative PN contributions that typically become stronger as you go to large orbital separations. So now you can think of a case where instead of an EMRI, you are observing an intermediate mass black hole. Those typically can even go to larger orbital separations like 50M. In that case, you really should consider environmental effects, because if you say that these dotted lines are important for the spiral, then certainly these type of ones should also be important. Now, most works that have been appearing in literature so far have sort of resorted to many approximations. This is because we didn't have anything better to do. But as LISA approaches, we should try to understand how much these approximations are valid. In particular, when we are trying to do stuff with EMRIs, we should always think of doing things in a relativistic setup because they spend so much time in a strong field regime of gravity by the large number of orbital cycles that they perform that they really probe relativistic effects. So doing things Newtonianly can many times give us, I mean, not wrong results, but not wrong qualitatively, but still for the precision that Lisa will have, they can be wrong in a quantifiable sense. And this is precisely the case of that study that I mentioned from Lorenzo Sperry. So in their study, they used AAK waveforms. These are basically an approximate waveforms where all the powers of all modes are projected into the quadrupole mode. And more recently, in a collaboration with Hassan Calvati, Alessandro Santini, also Lorenzo Sperry, Hassan, who is a PhD student in Perimeter, has developed a fully relativistic framework for EMRIs up to first order in the mass ratio, so adiabatic waveforms. But the full waveform is relativistic, is the important part here, which is not the case for the AAK model. And we repeated the experiments that Lorenzo Sperry did a few years ago, and we found that we could have much tighter constraints on these environmental effects. So here you should be comparing this left plot with the orange one. So you can see that we have an improvement of like a factor of 4 in the width of our posteriors. And the reason for that is that the AAK waveform that was used a couple of years ago, as you can see from this plot, so this is a waveform for the same EMRI system. So we pick precisely the same EMRI system, and we are showing the comparison between the AAK with the relativistic inspiral. This is the gray line with respect to the black line, which is a fully relativistic waveform that was developed. And you see that the AAK underestimates the relative power of the waveform on the early inspiral. But this is precisely where the environmental effects are more relevant. As we just saw, they are sort of negative PN contributions, meaning that if you fix the signal to noise ratio of your system, then the AAK will have less power in the early spiral, so it will have less power in the region where environmental effects are more important. So you will be able to constrain them worse. So this is a case where just by improving the relativistic parts of the vacuum section of the system, so this is just the waveform, we are not doing anything different with respect to the environmental model, you can see that we improve the constraints that we are able to put on these systems. Now, also all the results that I've been discussing are for circular systems, and there is an expectation that these EMRIs that are formed in AGN disks should be circular. The reason for that is that these spiral structures that are formed in migration effects can damp eccentricity very efficiently, more rapidly than the binary shrinks. But this actually has some caveats that I will now discuss. So there's a lot of missing physics on this expectation that we should consider, and that should make us thinking things a little bit slower. So first, all these migration effects that I've been discussing are sort of linear estimates that ignore short time variations, in particular stochastic variations on the torque that are coming from asymmetries in the gas flow near the secondary, that could be coming from turbulence from magnetic fields. And in fact, there's a recent study by Dertinsky and collaborators where they simulated an intermediate mass ratio inspiral in one of these disks, so fully numerical with hydrodynamical codes, and they measured the torque around the secondary compared with what the estimates are from migration linear theory, and they found that typically, which is what we are seeing here, the evolution of the torque follows the trend that we expect from linear estimates, but the order of magnitude can be a little bit different. It can even change sign. So instead of a torque that is accelerating the spiral, the torque is stalling the spiral. The gas is pushing the binary outside. And you can see that in the Latin spiral, so when the two bodies are very close to each other, the torque becomes a little bit chaotic. This is because the fluid does not have time to adjust to the spiral of the binary itself. So you can not longer assume some kind of adiabatic setup where the binary is inspiraling, and at every orbit configuration, the fluid has time to relax to a new stationary configuration. And what's interesting about this is that this kind of stochastic variations typically excite eccentricity in time. So this is the first mechanism that we see that, okay, linear migration will dampen eccentricity, but if we consider finer details in our modeling, this starts to be put in question. Now, the second case that is even more important, in my opinion, for this, is that the spiral density waves are not excited for large eccentricities. So to see that, we will consider a Newtonian model for our disk. So this is the typical Shakura-Sunayev thin accretion disk, where we can parameterize the disk by just three numbers. The first is the surface density of the disk, which has some central amplitude and a slope. And then we consider the height of the disk, or in this case, the aspect ratio, which is the height divided by the orbital separation. Again, there's a typical central aspect ratio. And if you consider that the disk is locally isothermal, then the slope is fixed by the slope that you pick for our surface density. So this is just a reformulation of the Shakura-Sunayev disk model. If you are used to see this, you probably see this parameterized by what is called the viscosity parameter or the accretion rate. I will make the connection with that later on. But for now, let's consider this parameterization. Now, the relative velocity of the secondary with respect to the gas flow can be computed by just this simple scaling. And you see that it corresponds to the ratio between eccentricity and aspect ratio times the speed of sound of the gas. This means that considering that the aspect ratio, so this h here, typically goes from 0.02 to 0.1 in the disk region where EMRIs are observable, so in the inner disk where we already are below 50 m, then for eccentricities larger than this h, the secondary will be moving supersonically with respect to the gas flow. And in this case, you can no longer excite these spiral density waves. So there are two different regimes in the system. The first is when the eccentricity is smaller than the aspect ratio. In this case, the EMRI is moving subsonically with respect to the gas flow. You can excite the spiral density waves and have these sort of global migration torques that are interacting with the binary throughout the full disk. When you are moving supersonically, so when eccentricity is larger than h, the dominant contribution from the environment comes from the local overdensity around the secondary. So you really have sort of a tail that's moving around your secondary. And this is really where the effect from the environment comes. And so these are numeric. So these are analytical plots precisely of these effects in the case of dark matter. So not in the case of a disk, but the same applies here. And what's important about this differentiation is that you can compute sort of analytical estimates both for migration and for this local dynamical friction using a bunch of approximations. So in this case, if you neglect density gradients, if you neglect the disk differential rotation, and if you neglect the Wake's curvature, this is what is called local approximation. And typically, it has been shown to work fine for the mass ratios of EMRIs. You find this table here. So this has been work by myself and other collaborators like Lorenzo Speri, Laura Sberne, Shuban, which I think is in this call. So it's we are currently finalizing a paper on this. So we consider the inner region of the alpha disk, where the slope of our density is given by this number here. So it's 3.5. So actually the density is increasing as you move further away from the disk, from the supermassive black hole. The aspect ratio decays with 1/r. We have our two regimes, and we see, and here I'm showing the the orbit average damping of the semi-major axis. So this A is not the black hole spin, is a semi-major axis, and the damping of eccentricity. And what you see, what I want you to focus here is that the functional form of these orbital average damping timescales are different when you are in the subsonic regime with respect to the supersonic regime. So you see, for example, for the semi-major axis, you have a dependence on migration on 1 over h squared, and here you have a dependence on 1 over h. The same here for eccentricity, you have a dependence on 1 over h0 to the 4, and here you have, again, a dependence on 1 over h. And now, going back to my argument that when you are moving supersonically, eccentricity is not damped that efficiently, you can see that by comparing h dot to e dot to a dot, so, or the typical timescales for this damping. So if you divide e by e dot divided by a by a dot, so this gives you the ratio between the damping timescale of eccentricity versus the damping timescale of the orbital separation. You see that for the subsonic regime, this scales as h squared. H is a small number, so again, between 0.02 and 0.1. So in the subsonic regime, indeed, we have that eccentricity is damped more efficiently than the binary is shrinking. But in a supersonic regime, the opposite occurs. So in this case, TE over TA is given by E over H, which in the supersonic regime corresponds precisely to the case where E is larger than H, meaning that this number, if you are really in the supersonic limit, will be much larger than 1. And in this case, the orbit should be shrinking much faster than eccentricity is damped. So again, we have this case where if you have one of these, recall the formation channel of EMRIs, if you have one of these EMRIs that is coming from a large separation on a very eccentric orbit, the binary will be shrinking, but eccentricity will not be so damped as this occurs. And this again poses questions whether binaries that are formed or EMRIs that are formed in AGN disks are really quasi-circular or not. Again, this is still a simplistic model, so we are ignoring a lot of stuff. For example, we are not considering relativistic effects. We are not considering the curvature of the wake in the disk. Even this model does not consider stochastic effects. Also thermal effects, which should be important at large orbital separations. This model that I showed is also only applicable for prograde orbits. When I say prograde, is with respect to the disk. So for retrograde orbits, things are even more complicated because in this case you can have excitation of eccentricity. So this makes sense if you think of something that is of the gas that is orbiting around in one direction, and now if you send an object on the opposite direction, it's like going on the opposite direction of a current. You should feel some push that is going to bring you to the direction of the current, and this is behind the excitation of eccentricity for retrograde orbits. Also, we are ignoring accretion of mass throughout the spiral, and all these effects should, in principle, change our model by a factor that goes from 1 to 10. Now, if you combine all of them, things may get complicated. But for now, let's just consider our improvement from the circular picture to the eccentric case and see what is the impact on observations. Now, in fact, this has been quantified last year in codes that do binary formation. They consider these nuance of having the binary moving supersonically or not with respect to the gas in the disk. And what they found is that, in fact, you can, so here you have the case of an EMRI that is forming at different inclinations from the same orbital separation with the same initial eccentricity. So you see that depending on inclination, which is going from smaller to larger, where in this case, when we have a large inclination, we are actually flipping the binary. So the binary is becoming retrograde. Initially, you can have excitation of eccentricity, and then at some point, the binary will become prograde with respect to the disk, and again you have this damping of eccentricity. You see that initially the damping is quite slow because the binary is still moving supersonically, and then at some point when the binary hits the subsonic regime, you have a more efficient damping. But even for the system, in this final radius where they stop the evolution, we are already at 40 m. So potentially this could be observable depending on the parameters of the binary. And in fact, there's a statement on this paper saying that since the eccentricity damping may not be as efficient as inclination damping, there might be some eccentricity residual on capture black holes for EMRIs. So again, this is not just something that we have been thinking. There are other people that have considered this setup and have reached the same conclusion that EMRIs in disks may not be that circular as previously thought. So we built again, when I say we, me and my collaborators, Laura, Lorenzo, and Shuban, build a phenomenological model for the evolution of eccentricity and orbital separation in one of these disks that is able to capture the analytic limits of the subsonic and supersonic regime. And then we build a global model based on feeds from hydrodynamical simulations. So this is a little bit, I would not say ad hoc, but there's a lot of uncertainties on this transitory region. So you could, for example, think of a case where instead of this bump in the orbital separation, you consider something a little bit smoother. We also consider these the variations, but the qualitative picture doesn't change. So let's just assume that this is our true model of the evolution of the binary in the disk. And now we repeat the experiment that Lorenzo and friends did a couple of years ago, where we consider a corrected inspiral, where we have the evolution from gravitational waves, but we are now introducing the correction from the gas, not just in the orbital separation as they did, because they consider circular orbits, but also in eccentricity. And we inputted this in our state-of-the-art waveforms using what is called the fast EMRI waveform package. So this is a package for evaluation of waveforms for EMRIs that is, as the name suggests, fast, and is also very modular in the sense that you can easily introduce these corrections in the trajectory of the inspiral and have a new waveform based on that. I mean, these are like 3 lines of code that you need to do. So you can consider other corrections that you want to study, like dark matter or beyond GR theories, if you want. And we input this on a Fisher matrix code, and we computed what is the precision with which we can measure the parameters of the disk. So in this case, the central surface density and the central aspect ratio for different disk configurations for the same EMRI system. So this is the same EMRI that Lorenzo considered a couple of years ago. We are now considering the eccentric extension for a disk with different densities and different, or in this case, the same height, but we also considered different heights. And you can see that if the disk is sufficiently dense, then you can constrain both the density and the height of the disk with a relative precision of 10%, which is amazing for astrophysics. You can also see that this depends on the initial eccentricity that you consider. So there appears to be an optimal eccentricity with which you can constrain things better. So this is precisely the eccentricity where we are having this transition from supersonic to the subsonic regime. So if you consider a different height for the disk, so here I was considering 0.025, you see that the optimal eccentricity is precisely between 0.025 and 0.5, because this is catching the transition from supersonic to subsonic. If you consider 0.05, then the optimal eccentricity with which you can constrain things better becomes larger, because again, now you are having the transition in a different region. And why does the transition helps constraining things? Well, because you are changing the functional form with which the parameters evolve. So you should be breaking correlations with the other parameters of the EMRI. So this is a case where, although our model becomes more complicated because, I mean, the form of the modeling is indeed not very analytic in some sense, but it helps doing science because even though the model is more complicated, being complicated breaks the degeneracies in the modeling of the EMRI. Now, if you have constraints for the surface density and aspect ratio, you can translate this into some kind of viscosity or accretion rates if you prescribe some modeling for your disk. So in this case, we consider the typical modeling for the Shakura-Tsunayev disk, where the surface density is related with these two parameters here. So this is the viscosity parameter. This is the accretion rate, so how fast the supermassive black hole is accreting matter, or how fast or how much per time is accreting matter. And then you can just translate the constraints that you got into constraints for these parameters. And something that is very important here is that we can constrain the accretion rates and viscosity simultaneously. And this is not possible for circular motion because there, these two parameters are completely degenerate. And this was the same for surface density and aspect ratio. So in the circular case, we can only measure an additional amplitudes in the evolution of the orbital separation. Here we can measure two amplitudes, the amplitude on the evolution of orbital separation and the amplitude on eccentricity. And using these, you can break the degeneracy between the accretion rate and viscosity. Now, why is it important? Because if you have an accretion rate and or if you have an accretion rate and you have a primary mass for your supermassive black hole, then you can try to combine this with electromagnetic observations to try to improve the host identification of your EMRIs. So a problem for EMRIs is that in the same sky localization, you can have different supermassive black holes from electromagnetic observations, and then you don't know which one corresponds to your binary. But if you now have more information coming from the accretion rate, you can try to combine that with AGN catalogs, for example, the one that will be built by the LSST, to try to reduce the number of possible hosts for your EMRI. And then you can, for example, do dark siren studies to try to measure the Hubble constant. Or you could also combine your EMRI observation with some kind of search for one of these quasi-periodic eruptions or quasi-periodic oscillations in the future, and actually have some kind of electromagnetic counterpart for your system. So this slide here is in blank because this is something that we are doing right now, so we don't have any results, but it's something that we are thinking of, and we could potentially have something interesting in the future. Now, another important question that we want to address is that, okay, I have my EMRI that is in the accretion disk, but now let's consider the case where I have the EMRI in the accretion disk and I have some kind of other beyond vacuum GR effect. For example, the case of a dipolar radiation coming from a scalar tensor theory, or I have some kind of variation in my gravitational content, for example. And it has been found in recent years that when you consider these multiple beyond vacuum GR effects simultaneously, it can be quite hard to constrain them because they become very correlated with each other. Now, this was a consequence of the fact that the modeling for these beyond vacuum GR effects is kind of simplistic. So it's just these power laws where you have an amplitude and a slope. And of course, if you start considering multiple power laws, then they will be very correlated. This is intuitive to think of. So now we can think, well, if my model is more complicated, in particular, if I have one of these transitions between supersonic to subsonic motion, then perhaps I can break these possible correlations between different GR effects. It's also something that we want to quantify in the near future. Now, how am I doing on time?
Yeah, you have about 10 minutes.
Okay. So in my final minutes, I will try to connect this with other astrophysical environments. So as I said, we don't need to just consider AGN disks. AGN disks are the ones that we know are between the observable universe, are the ones that are more dense, but we could also consider dark matter structures. And in fact, again, coming back to our expectation that EMRIs in astrophysical environments should be circular or not, dark matter distributions will typically have a flat density profile. So they will have constant density in some region around the supermassive black hole, or almost constant density. And it has been found that these kind of constant density structures will typically excite eccentricity. So again, this is one more case where we see that these wet EMRIs may not be that circular. Now, I've done some recent work on the evolution of EMRIs immersed in one of these dark matter environments that is composed by what are called ultralight scalar fields. So these are very light particles, which can have masses between 10 to the minus 6, 10 to the minus 23 electron volt, and that appear in the beyond standard model theories. In particular, they are motivated by string theory. And what's interesting about this form of dark matter is that on cosmological scales, they behave as particles, but because they are so light, the Broglie wavelength can be very large, and meaning that on sub-parsec scales, they behave as waves. And behind that, there's a lot of interesting phenomenology. Perhaps the most known is the case of superradiance, where if you have one of these ultralight fields around a rotating black hole, the field can extract rotational energy from the black hole and condensates into this kind of clouds. These clouds, they correspond effectively to bound states around your black hole because the field has some mass, so you have some kind of potential well where the field can be trapped or quasi-trapped. They are non-spherical, meaning that they will be emitting gravitational waves that can either be detected individually or through a stochastic background. So in fact, LIGO is already targeting this 10 to the minus 13 region. With LISA, we will be able to probe this 10 to the minus 18, 10 to the minus 17 electron volt region. And what's interesting about these clouds is that they can be extremely dense. So clouds around supermassive black holes can reach 5 to the 10 to the 2 grams per centimeter cube. So this is 50 times more dense than gold. So imagine that you are swimming in a sea of gold. The amount of friction that you will feel will be a lot. So now if you have a secondary object that is going around our supermassive black hole and it is feeling the friction from or accreting matter from these very dense environments, again, you expect some kind of effect to appear. Now, this has been quantified by both in a collection of works by me, Rodrigo Vicente, Vitor Cardoso, and Caio Macedo, and parallelly by Richard Brito and a student, Shah. So the rationale here is to compute what is the additional flux of energy that is carried away by scalar waves, and again add that to the gravitational wave radiation, and then you can recompute these corrected in spiral trajectories and try to do again data analysis with that. So there are two parameters. So I don't have time to go into in a lot of detail here, but there are two parameters that we want to quantify. One is the mass of our field, which is being here normalized by the black hole mass. And the other is how massive our cloud is, so the mass of the cloud. So we have two parameters, mu or alpha, which is the mass of the field, and b, which is the mass of the cloud, which can actually get to 0.1 or 10% of the mass of the supermassive black hole. Now, again, we included this in the fast EMRI waveform package. And at first, we just saw for which systems we could have a dephasing that is larger than one cycle after 4 years of observation with the EMRI. So I'm showing here two different EMRIs with two different masses and mass ratios. And I'm showing what is the minimum cloud mass, which for each mass of the field gives us one of these one cycle dephasing after 4 years of observation. So everything that is above these lines corresponds to larger dephasing. And you see that considering that our cloud mass should be always smaller than 0.1, then we could probe masses larger than, or this should be just a large, than 0.1. And this is precisely what we expect, where we expect superradiance to be very effective. Now, again, we included this in corrected trajectories, and we run a Bayesian MCMC analysis for this EMRI system. And we found that we could constrain the parameters of the clouds, so the mass of the field and the mass of the clouds, with a really, really, really large precision. And this is probably the most precise test that you can do to this kind of astrophysical environments, especially in this parameter region. Now, I have to give credit to Pippa Cole and collaborators, that did this a couple of years ago. Now, the main difference with respect to what they did is that they consider only Newtonian models, where here we are doing everything fully relativistic. So we don't have any direct comparison showing how much we can improve or what is the bias in just considering the Newtonian modeling, but it's something that we should do probably also in the future. Now, in my final minutes, I want to discuss how we can actually do this in LISA. So the analysis that I showed here is very simplistic. We just consider one source and we put some kind of PSD. But LISA will be much, much, much more complicated because in LISA we have to do what is called the global fit. So there will be thousands of sources juxtaposed with each other, corresponding to galactic binaries, massive black hole binaries, stellar origin black hole binaries, EMRIs. You can have other signals that we don't even know what they are. We also don't know what is the noise of the instrument, so we have to fit for the noise. So we have to fit all of this at the same time. Now, to do that, you need to pick the models that you want to include. And probably at first, people will just use vacuum GR models because that's the sensible thing to do. Now, then there's a question of how you can look for beyond vacuum GR effects, in particular environmental effects, in the context of the global field. So imagine that in 10 years, you have some kind of, you have built your own group and you are looking for environmental effects with LISA. You have two options here. You either include your beyond vacuum GR corrections in the global fit and you rerun that again. Well, for that, you need first, that's very expensive. It consumes a lot of energy and it will require a very high level of specialization of the global fit and also a lot of computing power, which I'll guess will not be available to everyone. So, but because these effects are sort of corrective effects, so they should contribute to small corrections to the global picture, you can think of trying to do things post-processing. So you use the residuals that come from the global fit, including only the vacuum GR models, and you try to see if you can search for beyond vacuum GR effects using that post-processing information. So this is also a problem that we are starting to look at. So how well you can, so the question that we want to address is how well we can do science using this strategy with respect to doing the full global fit, because doing the global fit is hard and expensive. So my final slides, what I want you to remember from my talk is that formation and inference of EMRIs in astrophysical environments is still in its infancy. So there are many things that we need to understand better for the purposes of LISA. But the overall picture that is arising in recent years is that every time we consider some final detail in the modeling, we get more interesting phenomenology. And this might be a problem, or well, not a problem, but makes the modeling complicated, but it also helps to probe these additional physics because it helps to break correlations between with other effects. But as I just explained, it's still unclear how we can try to study these additional effects in the context of the global fit for LISA. So something that I try to push for is that people working in strong field theory, people working in astrophysics, and people working in data need to talk more because for us to be able to probe this kind of additional physics that is unclear how we can do it and how we can even model it, we really need input coming from the theory part, coming from the observational parts, and we cannot be just divided between ourselves doing our work in our ivory towers, because if we do that, by the time Lisa flies, the theories will come with their theories to try to test, but we will not have any framework developed for doing the proper data analysis for those type of theories. So I hope that Lex also has a role in this, in bringing people together, and I'm looking forward to see the next talks in this seminar series.
Okay, great. Thank you very much for a very nice talk. So we have about 5 minutes for questions. If anybody has any questions at the end. Okay, so maybe I can just ask a very basic question because I'm not familiar with EMRIs at all. But how do you define a wet EMRI? What makes an EMRI
Yeah.
wet?
Oh, yeah, I didn't. I put the name, but I didn't say what they are. So dry emeries are the emeries in vacuum. This is just terminology that people came up with. So dry emeries are emeries that are formed and evolve in vacuum. So you just consider the isolated secondary and around your supermassive black hole. A wet emery, there is something more there. So they were first given this name in the context of disks, but I think they have been imported for the case also of dark matter, and even in the case where you have, for example, a third body that is interacting with your binary. So they have been called wet, they have been called dirty. People, colleagues of mine, both say these names are not very good. They have some kind of sexual innuendo. I've also proposed sweet if we want to change the name in comparison to dry. But yeah, that's just in a name.
Okay, so anything except vacuum basically is
Yeah.
a wet EMRI. Okay, great. Okay, so let me stop unless there are any more questions from the audience.
Yeah,
I will.
maybe, sorry, I was just curious if you could say something more when you discuss the local and global, was like friction, I think.
Mm.
I mean, when you say local, it's like it is going so fast that, yeah, that you said there is like a tail. It's going so fast that
Yeah.
they cannot interact.
Yeah, so when I say global, instead of going for the local, let me explain the global. So the global thing is that when you have a circular binary, you excite these spiral density waves. So you have the waves that are propagating outside the disk, right? And at specific locations that are actually far away from the binary, these spiral arms exchange angular momentum with the binary resonantly. So this is what is behind Lindblad resonances and so on. So when you are computing, what is the effect from coming from these spiral waves? You have to consider the full disk. You have to do a sum in all the possible locations for these resonances. Of course, as you go further away, they will become less relevant, but it's really an effect that's coming from the full disk itself. So that's why I call it global. It's a global effect. While in the case of dynamical friction, because you don't form these spiral arms, you really just have the local tail that is close to your secondary, and you can basically, I mean, basically the dominant effect comes from the things that are very close to the secondary. That's why I call it local. And this tail then decays its density as you go further away from the disk, from the secondary. So you can see it here. You have, in the supersonic case, you have the I tail very close to the secondary, and then there is the decay. So yeah, that's the difference here. Is that in one you consider, I mean, the main effect comes from density that is close, very close to the secondary. In the other, the main effect comes from a structure that is already far away from the secondary. And in fact, you cannot have In a supersonic case, you cannot have a local effect because of the symmetry between the front and back sides wake that you generate. They cancel each other out. So you really need the assistance from the rotation of the disk.
Okay, see. Thank you.
Okay, so with that, I will just stop the recording.